Hello everyone, welcome back to Math and Beyond and this podcast. Today it is the 13th, I think. Yeah, 13th episode. I don't remember precisely. 13th episode of Math and Beyond. Today we are going to talk with Cesare Cazzaniga. He is a PhD student in high energy physics at the ETH of Zurich. So I'm now going to send him the invite. Then we are going to talk about quantum fields, the standard model of particle physics, and more in detail about the Higgs Boson. So I will see you in a second. Hi, Cesare.
Hi.
Hi, how are you?
Fine, thank you. And you? Are you
Great. Yes, I'm doing great. There is a lovely sunshine today in Amsterdam, so definitely a great day. Yep.
Okay. Also here in Geneva is quite nice. Yes.
Okay. So why are you in Geneva?
So I work in Geneva at CERN, but then I'm affiliated with the ETH Zurich. So let's say once a week I go there for the teaching, but I am stable in Geneva to work.
Okay. I indeed said before, I gave a small introduction about our topic of discussion, the standard model, the Higgs boson, and I gave you an introduction about you. So correct me if I'm wrong, you studied physics in Milan, right? As a bachelor degree, and then you came to Switzerland to do master degree in high energy physics, which is the topic that you are now doing your PhD at the ETH of Zurich, right? Mm-hmm. And you have also been working at CERN, as you just told us, and we can see from the T-shirt, very nice. Okay, so I think we can jump into our discussion, and I will ask you firstly, what is the standard model of particle physics, which is a very non-exciting name. Let's put it this way. It's really non-exciting, but physicists do tend to get very much excited about this model. Why is that the case?
Yes. So let me try maybe to share just a couple of. Can you see?
Yes.
Okay, so maybe let's go to the question that you asked, and then maybe if we want to talk about LHC and what we do at CERN, we can go back to that. But basically, this standard model of particle physics is the theoretical model that we use in particle physics to describe matter and radiation and how the matter interacts with itself, basically. So here in this table, which is really the usual one, you see the main building blocks, if you want, of matter, and also then I will talk about how radiation itself can be made up of particles. So if you look, for example, at the box on the left, the blue box, basically there you see the fundamental building blocks of matter, which are quarks and basically what we call leptons. So the quarks are the ones grouped in the violet tables, while the leptons are grouped in the green tables. And there are different kind of flavors of these fundamental particles, but the main idea is that these fundamental fermions have a specific characteristic, which is being spin 1/2 particles. Then they have a different type of charges, they interact in different type of ways, as we will see later. But the main idea is the fundamental building blocks of matter are fermions. And then these fermions, especially the quarks, will compose more complex states like protons and neutrons, just reassembling in a very specific way. And then, if you look also a bit in the table at the center, there you see the fundamental antimatter fermions. So for each fermion, there is an antimatter counterpart, and it is, if you want, kind of natural consequence of the theory that is at the basis of the standard model, which is the quantum field theory, that maybe then you want also to talk about. And finally, on the right, you see these force mediators or gauge mediators, and these are still described in by particles, if you want, and these particles, these gauge mediators, are exchanged between the fundamental fermions. And this exchange of force mediators is what we then use to describe the main interactions that we know in nature. In the standard model, we describe basically 3 types of interaction. Then gravitational one is let's say another topic, a really difficult one, which is not at the moment within our model that describes particles and their interactions. But okay, this is a general outline of what the standard model is. And okay.
So you just mentioned the quantum fields. Which is, let's say, a topic, a word that I would see quite recurring quite often while reading about the standard model. But what are quantum fields? What do we mean by them, and why are they related? Why are quantum fields related to the standard model of particle physics?
Yes. So as I was mentioning before, basically the standard model is nothing but that a model based on a theory. So there is a difference. We have a general theory, which is quantum field theory, that now I will talk about, which is the theoretical framework we use to describe any type of interaction with any type of fields that now I will mention. And the standard model is just a specific quantum field theory, which we found to describe very well the real world. And it's based basically on observations. So that's why it's a model, and it's not a theory itself, the standard model. So quantum field theory comes from a very, let's say, long process. So the concept of field itself, let's say, was introduced, if you wanted to avoid this action at distance or interaction between matter at distance that at the very beginning came out when formulating theories of interactions like Newton's theory, or if you want, then also electromagnetic theory. But in the electromagnetic theory itself, this concept of field became really physical. So in the electromagnetic theory formulated by Maxwell and others, of course, what you find is that at the end you can describe forces via fields which are extended in the whole space, and you can describe the action of the force by means of this quantity, this object, in each point of the space. And these fields themselves can be generated by some object that can be, in the case of the electromagnetic field, the electric charge, and then can even, let's say, propagate independently from the source itself. So with the theory of the electromagnetism, if you want, the concept of field became really physical with the electromagnetic waves and the prediction of the electromagnetic waves. Then, let's say this theory of electromagnetism was really at the basis of special relativity. So special relativity is based on the theory of electromagnetism, and the very famous Lorentz transformations at the end are just obtained requiring that Maxwell's equation still have to, let's say, be valid in all systems of reference. So basically, if you take a systems of reference and you calculate the Maxwell equation, or you write the Maxwell equation, then these equations must still be valid in another one system of reference, which is related by the first one by some, let's say, relative velocity. So special relativity basically adopts and is built on Maxwell equations and electromagnetism. At the same time, what happened is that another theory, which was really different, came out, and this theory is the theory of quantum mechanics. So in that case, the theory is very different from a mathematical perspective, and also, if you want, conceptually. So it is completely far apart from special relativity, and one of the main problems was really to try to have a quantum theory which has inside also special relativity. And at the end, quantum field theory is this kind of theory. So the way to try to unify the two theories in a consistent theoretical framework is to introduce fields extended in the full space-time, which are quantized. And you need quantization of the fields to have particles, and to do particle physics, and to, if you want, calculate transitions, amplitudes between an initial state with a certain amount of particles and final states with a certain other amount of particles. So the quantum field theory at the end is the way to unify these two theoretical frameworks, which were very far apart, and the procedure to do this is called the second quantization. I don't want to now go into the details of what the second quantization does, but let's say for those who are more interested in the formalism, basically, if the first quantization you introduce some commutation relations between, if you want, your space coordinate vector and momentum. In the second quantization, basically, you introduce non-trivial commutation relations between the fields themselves that then are used for defining basically the quantized fields. So if you want,
well, when you say sorry, Cesare, when you say non-trivial commutation relation, right?
Yes.
What do you mean?
So basically, the first quantization, if you want, is based on you take x, and which is your coordinate, and p, which is your momentum, and you promote them as operators, okay, living in a certain vector space, which is called, I mean, in this case, these operators will act on, let's say, a function, and they live in a Hilbert space, let's say. So this is what is done in the first quantization. And non-trivial commutation relations means that if you take these two operators, x and p, and you calculate x times p applied to the wave function minus p times x applied to the wave function, you find something which is not zero. And this is basically the main principle of quantum mechanics, because out of it you can prove the famous uncertainty principle and all the main aspects of quantum mechanics. With the second quantization, what you do is basically the same, but instead of doing on coordinates and momentum, you do it on fields, which are, if you want, functions, and they are promoted in the second quantization to operators, and you introduce non-trivial commutation relations between these operators, meaning that when you calculate commutations between these operators, these will not be zero, and this then stands at the basis of what a quantum field is and how you can create out of it particles and antiparticles, if you want.
Okay, but why do we say that? Why do we say, or what do we mean when we say that particles are just excitation of the field, of the quantum fields?
Yes, this is exactly the point at the end. So, if you want, I mean, it's difficult to explain it with some common wording, but yes, the idea is exactly that one. So you can basically create out of the vacuum particles, and these particles are always associated to a given quantum field. So the space-time, the full space-time is filled with different type of fields, which can be an electron field, a muon field, a photon field, and all of these fields can be excited, and this excitation creates, or if you want a perturbation, creates basically particles. And interaction between fields also creates particles. So there is no, let's say, other way to picturing this out, because at the end is a kind of a formal thing, but I think, yes, this is the most...
Okay.
It's not trivial to explain it with some picture in mind.
Sure. But what do you mean when you? Well, sorry. What do you mean when you say the photon field? Isn't the photon field, or is not the photon, let's say, does not the photon arise from an excitation of the electromagnetic field? Why do we have different fields for all different particles?
Yes, so this is because, as I was mentioning before, so basically you want to explain somehow with this field theory at the end particles. So particles can have different kind of spins. You need a specific photon field because the photon itself will be a particle with a given spin, which is spin 1 in this case. So you need to introduce a vector field, it's called like this in the context of quantum field theory, in order to explain a photon-like field. Then you need also other things, because you need to reduce, let's say, the number of degrees of freedom for this field and so on, to give it the meaning of photon itself. But the meaning is that, as I was saying, you introduce different type of fields, because you then have to relate them to different type of spins for the particles. So matter fields or fermionic fields are formally much different compared to vector fields describing the photon. And there is no commutation relation indeed for the matter fields, but there is an anti-commutation relation from which one derives basically the Pauli exclusion principle for particles. So if you want the spin statistics, what was at the end the Pauli exclusion principle is explained at the level of quantum fields, introducing instead of commutation relation between the fields, anti-commutation relations. And you can do it only, let's say, having a specific mathematical object to do this. So you cannot use vectors, but you should use something different to define these anti-commutation relations, which is really what define a fermion field. So yes.
Okay.
I don't know. I don't know if you want me to be more explicit, but then maybe we go too much into the mathematical detail. I don't know.
Sure, indeed. Now, I want to ask now. Let's say some years ago, I don't remember. 2015? No, I don't remember how many years ago. We have had some major breakthrough, and we said there were newspaper, I guess, saying we found a new particle. It's the Higgs particle. What is this particle? Out of this, we can also think, we can also believe it was quite an important event, because a Nobel Prize out of it has been awarded to Peter Higgs, the theoretical predictor, the person who predicted this particle. But what is this particle? Why has it been discovered so late compared to his, let's say, cousins? And what is the role of the Higgs boson within the Standard Model?
Yes, so let me start maybe from, let's say this. So let's start from the fact that you can, let's say, introduce interaction in this Standard Model, basically let's say imposing some symmetry at the basis of the model. And this symmetry is represented with this SU3C times SU2L U1Y. So this is the general gauge group of the Standard Model, which is a product of Lie groups. Now, I don't want to go in the detail of what is the definition of Lie group, but the point is that these groups really define what is the symmetry that you want in your quantum field theory, and in this case, the Standard Model itself. And this symmetry generates interactions inside the Standard Model. The interaction that generates are basically the weak, the strong electromagnetic interaction, which are those that we observe experimentally. Now, the main issue is that once you impose this symmetry at the level of your quantum field theory, then this basically does not allow to write terms in your model which are related to mass. So you cannot introduce in the model, no way, masses which are compatible with this kind of symmetry. That, on the other side, explains very well interactions. So what you do is basically to try to introduce some mechanism, which is this Higgs mechanism, which at the end allows you to produce, let's say, these mass terms, breaking the original symmetry of the standard model, and this is what basically is the Higgs mechanism. So many times people, let's say, try to picture it in many different ways. So sometimes you have this snow field that is like the Higgs field, which permeates the whole space, and there are different type of particles which goes through this field, and some of them, if you want, will leave deeper footprints in this snow compared to the others, and these therefore will differentiate between particles which have high mass compared to particles which have lower mass or even are massless. So the Higgs boson itself is nothing but that, if you want, a perturbation or a quantum of this field, which is the Higgs field, which permeates the whole space. And so the original question, yes.
To interrupt you very quickly to understand that. So basically, okay, the Higgs particle is the Higgs relating to the Higgs field, but the Higgs field is the one through which the Higgs particle, let's say, gives mass to particles interacting with the Higgs field.
Yes.
Okay, sorry.
Yes. So before you were mentioning, basically, yes, that at the end we discovered this particle, which is this quantum of the Higgs field, and this was in 2012. So why was it so difficult to discover this particle? Well, let's say, to discover the particle itself, you need to, first of all, try to produce the particle somehow. And this is why we need particle accelerators and colliders. So you need a certain amount of energy to produce this particle, which is relatively heavy. So in the previous accelerator, which is LEP, which was an electron-positron collider accelerator, basically you could not produce the Higgs, and because the center of mass energy was too low, so people went very near to the center of mass energy, which would have been enough to produce the Higgs, but was not sufficient. So what people did at the end was to build another machine, which is a proton-proton collider, which is LHC, which allows to reach such a center of mass energy and produce the Higgs. Then you have to somehow see the Higgs, and you don't see the Higgs itself, but you see the decay products of the Higgs. So the Higgs will be produced by this proton-proton collision, but then you need to identify the decay products and go back to try to reconstruct the mass of the particle that gave these decay products. So here there is a sketch of CMS, and basically this is our, if you want, photo camera that we use to identify different particles produced within these proton collisions. And basically the detector is divided in different layers, as you can see. And these different layers of the detector are used to identify different type of particles. So you can identify the tracks of the particles in the inner layers, and then there is a layer to identify electrons and photons, and then hadronic final states in an outer layer, and in the outmost layer you have the identification of muons. So when you look for the Higgs, basically you look at some decay products that you expect to appear very evidently in the detector. And so people looked at, for example, Higgs decaying in 4 leptons final states. Is not really direct decay in 4 leptons, but is mediated by some other particles, which are Z bosons. Or these Higgs to gamma gamma final states, which again is not the Higgs directly coupling to the photons, because photons are massless. So you need some other non-trivial, let's say, process happening between the Higgs and the photons. But this was the second, let's say, final state that was used to try to discover this Higgs boson. And what you do is, as I was mentioning before, start from proton collision, collect final states, which will be or your 4 leptons or your photons. And from these final states, you can reconstruct the momenta of the particles that are measured in the detector, and then finally calculate the mass of the original particles that decayed in the final states that you observe. And if you are lucky, then...
Sorry, Cesare. So is it a, let's say, sort of reverse engineering from the effect that we see of the, because you said we don't see the Higgs boson, we see the decay, so an effect that the Higgs boson has. So yes, we measure the effect, we collect the data, we reverse engineer, and we compute our the data, the measurement that we want. Okay, understand.
Yes, exactly. And what happens is that if you're lucky, you find some bump, as was found at the end, in this mass spectrum that you calculate. And so basically, as I was mentioning before, this plot shows what was the situation before the discovery of the Higgs. So there you have on the x-axis the mass of the Higgs, let's say. On the y-axis, okay, forget about it. Otherwise, we go too much in the detail. But let's say the yellow area represents the excluded area, or the excluded masses for the Higgs boson. And this was before the discovery of the Higgs. So you see that basically there is a low region for the mass of the Higgs, which is basically excluded below 114 GeV. And then there is a small window at, let's say, higher masses. And people found at the end the Higgs boson between these two yellow regions, so around 125 GeV. But this was just to say that, let's say, people tried to access the Higgs boson even before the LHC, but they were limited by the experiments that they were running themselves. So the lower region exclusion is given by this electron-positron collider that existed before LHC, and managed just to arrive really 10 GeV less than what was necessary to discover the Higgs boson. And so, as I was mentioning, then there are different channels in which the Higgs boson was discovered, and the two main ones are the 4 leptons and gamma gamma, let's say. And this is very weird intuitively, because if you take the standard model and you calculate the decay branching ratios of the Higgs, so the probability that the Higgs decays into photons or 4 leptons, basically this probability is super low. So why people looked at the Higgs in decay channels which are not favored from, let's say, probabilistic point of view of the Higgs decaying into these final states. And this is because basically these final states, for leptons and photons, are very clean from an experimental perspective, and therefore, at the end, even if you lose a lot in terms of how many final states you will collect, so how many Higgs boson will decay into these final states, you gain a lot in terms of cleanness of the process that you are looking at, because of course at LHC you don't have only the production of the Higgs boson, but you have many other processes happening, and you have to find the Higgs boson, which is a very tiny signal inside a sea of background processes which can, let's say, look like the Higgs boson signal. So having a clean signature was really one of the key points. And here you see, let's say, the signal of what was called a new scalar particle around 125 GeV, both in the 4 leptons and gamma gamma, and this was found by both the CMS and ATLAS experiments at the LHC. So this was, let's say, the discovery that happened in 2012, and that people were really waiting for a lot of time, and that at the end led to the Nobel Prize for Engler and Higgs.
Pretty ironic that we do celebrate the Higgs particle where we actually do not even see the Higgs particle, we do see the decay of it. So
yes, so the thing is that so this here, if you want, is just telling us that there is some particle which has a mass of 125 GeV, and that was not there in our tables of particles before. Then what you have to do is to try to understand if this particle is compatible with our theories. And so you study all the possible production modes, decay processes of these particles, and you try to compare the theory with what you observe and try to characterize better the particle.
Okay.
So indeed, was not at the end, at the very beginning, said in the paper, the Higgs boson, but they were a bit more conservative.
Okay. And you mentioned basically before you mentioned the role of symmetry. Can you, let's say, spend some time to describe what is the, let's say, overall and even more specific, the role of symmetry in the standard model, and how does symmetry relate to the interaction of a particle or forces?
So this is the symmetry so that I was talking about. So this is let's say a way to introduce at the end, as I was mentioning, interaction. So now the point is how you do this, because it's not let's say so straightforward. So you write a model. This model is represented by some, let's say, expression, which is called the Lagrangian of the theory. This Lagrangian, in first approximation, describes how fields propagate in space-time. And that's it. So if you don't introduce any, let's say, symmetry in this Lagrangian, so if you don't impose that field, the Lagrangian is invariant under certain transformation which belong to a certain symmetry group, which is, in the case of standard model, this one, you don't have interactions and you don't have any possibility to describe interaction between the fields that you write in the Lagrangian. So you just have particles free propagating in the space-time, or if you want, fields. So in order to produce interaction terms, so having really in the expression of this model some terms which you see couple, if you want, different type of fields and therefore describe the interaction, you need to require your model to be invariant under certain transformations, which need to be this local gauge transformation, meaning that you can redefine, if you want, the fields in each point of the space-time via a global phase, via a phase transformation. So if you want this phase transformation of the fields, it can be defined with a different phase in each point of the space-time. This is the concept of, let's say, symmetry. It is a kind of abstract, but basically, at the end, you end up with a Lagrangian like this one that really describes not only fields freely propagating in the space-time, but also the interaction between the fields themselves. And you cannot do it in a consistent way in other ways, basically. So I don't know if, let's say, intuitively is not really easy to explain.
Sure.
But from a mathematical perspective, defining invariance of your model under certain transformations allows you to introduce new terms, like the ones that you see here, that basically describe the interaction between the different type of fields. And there is no other, let's say, consistent way to do it.
Okay, so to see if I understood properly, when you say that we need to define our Lagrangian to be invariant and transformation, what, let's say, said brutally, we mean we can take, let's put it this way, we can take the field, we can stretch them, or we can squeeze them, we can manipulate them. The interaction of the particles within our standard model would have to, let's say, be symmetric, meaning yielding the same result. Is it sort of correct?
So yes, I mean, let's say, brutally, if you want,
very, very brutal.
Very, very brutally, yes. Let's say you need, if you want, to describe a certain type of interaction between different fields. To be able, you need to be able to redefine the fields with some certain type of transformation, such that the physical observables that you calculate later after this transformation will not be dependent on how you redefine the fields. So basically, what I said is more or less compatible with your statement at the end.
Okay, and yeah, it's I understand it is very, let's say, mentally, let's say, challenging to grasp. But if I think about it, I mean, at the end of the day, we are trying to understand basically everything that is happening around us. So maybe if it was immediately easy to grasp, then maybe it was not the right theory. But okay, so I would like to let's say ask you some let's say some let's call it an open problem, open question. Let's say about the Higgs field, about the Higgs boson, and what is let's say still unknown about the Higgs sector, so the Higgs particle and the Higgs field. What we know that we don't know, and why is it important to understand what we know that we don't know, and indeed the parameters?
Yes. So first of all, just starting from this picture here, this is the model that basically, this is the standard model, and there you see that you can describe the full interactions between particles with 19 parameters, and 15 of them basically come from the Higgs sector. So knowing the Higgs sector, I would say, is quite important within the standard model. And what are the let's say, what people are doing to understand better this? As I was mentioning before, they are trying to look at the Higgs in different type of production mechanisms. Here you see some, let's say, very famous Feynman diagrams for production of the Higgs boson and decay mechanisms. And I mean, I will not go through this, but if you look at the, let's say, developments from the discovery of the Higgs boson to nowadays, there was, of course, this gamma and 4 leptons discovered, but then people started to, let's say, try to look in more, let's say, the couplings of the Higgs with, for example, different types of leptons or quarks, especially those which are heavier. Because of course the Higgs couples much strongly with heavier particles. This is the, let's say, the main concept of the Higgs and how it couples with particles. And if you want, here you see very well what is the outcome of this search. So if you take the y-axis, there you have the coupling of the Higgs with a certain particle, and then on x-axis the particle mass, and you see basically that people try to look at how the Higgs couples to the muon, to tau leptons, b quarks, the W boson, the Z boson, the top quark, and all these measurements basically are in well agreement with the dashed line, which is the standard model prediction, let's say. So now there are, let's say, challenges related to try to fill even more this plot with other decays of the Higgs, or the other challenge is to try to see if there are deviations in the couplings of the Higgs boson. Because if this deviation, if there is a deviation in the coupling of the Higgs boson with a certain particle, then this would imply that the Higgs may be coupled with something new, which we don't know, and this alters then finally the coupling with the standard model. And so people are also trying, as you can see brutally in these plots, to see deviations, to measure deviations, possible deviation of the couplings of the Higgs boson and compare them with the standard model. So these, in terms of the Higgs sector, are the let's say developments, what people are doing. There are also, let's say, other approaches like effective field theories. So the idea of these effective field theories is to try really to look at deviations of the Higgs interactions coming from a general new physics. So you don't really specify what the new physics is, but you try to build a way, which is this effective field theory, to be sensitive to any kind of general possible new physics, living at a very high energy scale and affecting what we see in our lower energy scale, which we try to probe at proton-proton colliders. So I will not, let's say, go through this unless then you want to speak about that, but these are the main subjects as far as developments in the Higgs. Then there are open questions that you were waiting for, and these open questions regard, for example, dark matter. So we know that the composition of our universe is 5% standard model matter, and then there is this around 25% of dark matter, and then you have even something more, let's say, elusive, which is this dark energy. So this is one topic, and maybe the Higgs boson itself can be a portal between the standard model, so the matter that we see, and this hidden sector or dark sector of dark matter. So this is something that the people are exploring, or if you want, why we are in a universe dominated by matter. This is another open question, dominated by matter compared to antimatter, I mean. Or why, how, let's say, the neutrinos come into the picture of the standard model, because in the standard model, the neutrino have no mass, but experimentally we observe that the neutrino should have a mass. And therefore, this is, let's say, if you want, a kind of hint of physics beyond the standard model, but that at the moment we cannot really explain very well. So there are theories trying to address this question of the neutrino masses, but it's still an open issue. Then why the Higgs boson mass is so small compared, for example, to higher energy scales? And this is the so-called hierarchy problem. How gravity comes into the standard model, because now we don't have any hint, let's say, we have hints of how to have a theory, consistent theory for gravity also, which is a string theory, but then we don't have at the moment ways to test predictions for this theory. Is there a way to unify all the forces? So I have explained before that there is this general symmetry group, but can we even go further and find a unique symmetry group describing the Woolly interactions, which embeds the standard models in the symmetry group? So there are many open questions, and most of these open questions are really related to the Higgs sector itself. So, yes.
Okay. How can we, let's say, you mentioned before, going beyond the standard model, let's say, going towards a new physics, and I've read that we would, let's say, like, or we're trying to go towards new physics through the as you said, a high precision measurement of the Higgs sector, because as you said, many of those open questions were related to the Higgs sector. But how can we do so? So go to a new physics through new and precise measurement of the Higgs sector.
Yes, this goes again in what I was mentioning before, but let's go through it a bit more precisely. So let's start from a very simple example. So before the formulation of the standard model, there was a theory which didn't know about, for example, W boson, Z boson, but managed to describe basically the decay, the famous beta decay, and this, which is exemplified on the left part of the slide. So this theory didn't know anything about W boson, which today is what we use, is the mediator that allows this weak decay and the beta decay, but managed to introduce a theory, let's say, that describes this kind of decay without knowing about the W boson. So this was a first, let's say, a first approach of effective field theory. So what we want to try to do is to start from the standard model as an effective theory, meaning a theory that really holds at lower energies, and then at higher energies there will be another theory that we don't know, but this other theory can lead to some effects to lower energies, and so modify the lower energy theory, which is the standard model. This is the idea of effective field theory. So what you do is to take your standard model, Lagrangian, and basically add to it other terms, which are very general, and parameterize all possible effects coming from higher energy physics that you cannot access, but you can probe indirectly the effects. So what I mean is exactly in this plot here. So you try to reconstruct some mass of a certain particle, but this particle is too heavy to be produced at the LHC. So you cannot access, if you want, the right part of the plot, this red peak here. But what you can do with this effective field theory is to try to probe the effects of the tails of this distribution. And this is what people are doing. So trying to access minimal deviations in the standard model predictions for the Higgs sector. So to access, let's say, at the end, possibly to some constraints on the new physics scale. So measuring the Higgs sector parameters at the end gives you the possibility to set constraints on where you expect the new physics to happen. So if you don't see any deviation from the standard model prediction with this theoretical framework called effective field theory, you can say, okay, I don't expect new physics to happen until a certain energy scale.
Okay. What do we, let's say, as we proceed further above, actually up energy scale, and we reach let's say, Planck scale. Yeah, what can we expect from this scale with regards to the Higgs boson mass?
So this is the problem that I was mentioning before. So here, basically, the main is a kind of theoretical issue, this one. So in quantum field theories, you have the possibility to, let's say, calculate corrections to your predictions, because at the end, what is used is perturbation theory. So the prediction is in terms of an expansion on a given, let's say, quantity, which is in this case a coupling constant. So you can decide to truncate the expansion at a certain point, or you can decide to go farther in the expansion. Okay, and if you go farther in the expansion, in the case of the Higgs, you find that there are very large corrections to the Higgs mass that at the end basically will lead the Higgs mass to stay at the Planck scale. So the corrections are so large due to these, if you want, higher order effects, that the Higgs mass itself should be drawn at the Planck scale. And therefore, this is the so-called hierarchy problem. Why we observed an Higgs mass of 125 GeV while we have a Planck scale which is much higher, and it is possible to solve this problem, let's say, because itself, staying within the standard model, this would imply just trying to fine-tune the parameters to cancel out this very large correction. But this sounds really not natural. So within the standard model, you can try to define the parameters such that these very large corrections at the end will be cancelled, and you end up with the Higgs mass. But as you can see from the picture in the slide, basically it corresponds to really fine-tune your model, which sounds very unnatural, and for many theorists this cannot be acceptable. So what people did, for example, was to pass to another theory, which is more complex, and which associate basically to each fermion in the standard model a boson, and to each boson a fermion counterpart, and this theory is called supersymmetry. And with this extended particle spectrum and field spectrum, basically you can cancel the large corrections to the Higgs mass, and basically have the Higgs mass stable at the electroweak scale, which is, let's say, the energy scale that we are observing for the Higgs boson. So let's say it is still a very technical, theoretical problem, but this was one of the main motivations that lead people to formulate supersymmetry. And then supersymmetry, gives a lot of other, let's say, advantages, like you can try to unify the couplings that you have in the standard model in just one coupling for all the three interactions, and this will happen at a scale C, let's say, near to the Planck scale, a little bit lower. You can introduce dark matter candidates in this theory. So it's more complex theory, but solves some of the issues that I was mentioning before. The only problem is that we didn't find supersymmetry where we expected to find it.
Okay. And can I ask you, how does supersymmetry, let's say, planets, because I am reading the last point. How does, let's say, it opens towards a new theory, a theory of gravity? How does it plan to do so?
So in supersymmetry, you can basically introduce the graviton and what is called gravitino. So these naturally appear in this theory. So it's absolutely possible. Then the problem becomes how you find this kind of particles, and this is not trivial, let's say. But these are absolutely possible inside the supersymmetry. Then let's say there are more technical issues related to how to define a supersymmetric theory which is fully mathematically consistent with the inclusion of these gravitinos and gravitons, in the sense of perturbation theory, let's say. But you can introduce them. Probably the best theory to introduce this kind of new particles is a string theory, but string theory still has inside the supersymmetry. So yes.
Okay. I wanted to ask you that more towards the end, like after the next question, but then I'm going to do it now. What do you? Okay, because you are involved in particle physics, and which you showed us the table of fundamental elementary particles, which should be point-like, meaning they do not have any, let's say, interior components. Okay, they are the building blocks of everything we see. But then here comes string theory, and I firstly want to ask you: string theory yes, string theory no, and why yes or why no?
So
because I know there is a lot of let's say a lot of excitement around string theory. There surely is a lot of excitement, but there is also a lot of skepticism. There are many people being skeptical and not really attributing to string theory any, let's say, unifying power. Let's put it this way. What is your take? String theory yes or string theory no?
So let's say I'm at the end an experimentalist. So it's really important for us to have some predictions that can be verified experimentally. So I had a course in string theory when I was doing my master, and I found it really amazing from a theoretical point of view. You see that many issues, especially related to these divergences that you have in quantum field theory when you do perturbation theory, disappear when you pass to strings. And this is really amazing, and you can really consistently introduce gravity in this theory. It's fine. So for me, probably it's really nice to have this kind of theoretical apparatus. I'm a bit skeptical on how you can try to test this theory with the current technologies, let's say. This is.
So do you believe it is only, let's say, which of course it has its relevance, surely, but do you believe then it is mostly an engineering problem, meaning that we cannot test it, hence we cannot infer, or does it also have some, let's say, theoretical based inconsistencies? Because I've been actually yesterday I watched an episode of Lex Friedman podcast with a string theorist, and he was mentioning how many, let's say, results which in previous, let's say, physical models we had to fine tune. Some physical results do actually emerge spontaneous, as for example the graviton. And so, do you believe then it is just an engineering problem? Okay, at the moment it is not correct because we cannot test it. Theoretically, it is fascinating. So we will see in the future how our, let's say, technologies will develop, and maybe it may have a chance. Or do you also believe that theoretically it may still give, let's say, inconsistencies and problems?
So I'm not that expert in string, let's say, the theory behind. As I was saying, I did a course on that. Probably there are some, if you want, let's say, choices that you do in string theory that are not fully no, I don't want to say justified, but they are a bit arbitrary. Okay?
For example?
Especially when you try to, let's say, when you pass to superstring theory and you try to eliminate some unphysical state introducing some procedure, let's say, to do this, to have exactly the right balance of fermionic states and bosonic states. That way of approaching with that kind of procedure, to me, when I studied that, seemed to be at least arbitrary. But then there are many other aspects, especially related to gravity and the treatment of divergences, which seems to be solved by this theory. So from a theoretical point of view, on my side, I found some arbitrariness, but I'm not really the expert on the field to tell you that this is exactly the case. Probably you can find someone more expert than me on string theory.
Okay. I was also reading about, let's say, some other open question, and there appears to be this fundamental problem that we know how the Higgs boson, the mass of the Higgs boson, is fundamentally related to the state of our universe. Can you explain a bit why is this the case? What do we mean when we say that our universe is fine-tuned? The state of our universe is fine-tuned with the mass of the Higgs boson, and how can this, let's say, how can we explain it? Because sure, fine-tuning in the history of physics happened many times, but can we let's say wrap our head around why this time was the case?
Yes. So what I was mentioning at a certain point, yes, was this Higgs mechanism, and the fact that in order to solve the problem of the masses in the standard model, at the end, what you do is to, let's say, give to this Higgs field a potential, which is pictured on the left, this Mexican hat potential, where basically the minimum of the potential is non-zero, and is non-zero, and therefore, if you want, the vacuum expectation of the Higgs is non-zero at that minimum. So when you do this thing, basically this allows you to produce masses inside the standard model. The only problem is that we know from experimental perspective this potential only let's say at the level of the second derivative. So basically when we measure the mass at the end, we are measuring the second derivative of this potential, but then we don't know very well what is the real shape of this potential. In the standard model, we have a guess about this shape, but we don't know. And to measure more precisely this shape, there are let's say some proposals which are, for example, measuring the cupping of the Higgs with itself and these kind of things. But then another problem is also related to, let's say, the possibility that this potential maybe has other minima. And this seems to be, let's say, one of the outcomes of some studies. So according to some studies, it's possible that maybe there is another minimum of the Higgs potential at a very, let's say, at a much higher energy scale, which is actually the global minimum. So what basically we are living in a local minimum, and there is the possibility that at a certain point maybe our universe will tunnel from this local minimum to the global minimum of the Higgs, and this is strictly related to the parameters, if you want, of the model. So if you look at these plots, here you have on the x-axis the Higgs boson mass, and on the y-axis the mass of the top quark. And then you see, I circled it in red in the plot on the left, but in the plot on the right is just a zoom of that, where we are. So we are basically in a region which is between what is called metastability, so the possibility to have this second global, let's say a global minimum, which is not our minimum. So metastability and stability, so our minimum is the global one, so the green. So it seems like measuring the parameters of the Higgs boson mass and the mass of the top quark, we are living in that kind of situation. And
We're quite lucky.
Yes, exactly. And so people, let's say, first of all, started to question what is the probability that, for example, you will have a tunneling from our vacuum state to the other one, and this probability they found it's really small, so basically negligible. So we are kind of safe in this sense, but opens to the question, what is the meaning of having this tuning of the parameters in some sense? So what's the meaning of having our universe really at the edge between these two boundaries? This is, let's say, a question that people start to ask themselves. And this can open to really also metaphysical, if you want, interpretations, like, for example, multiverses. So maybe there is no really meaning in this setting of the parameters in our universe, because this is a specific settings, and in other universes you have other settings, and all of them are realized in all their possibilities. Or some people tried even to go further with this speculation, saying that basically phenomena at the boundaries are attractors in this multiverse. So sometimes there is this kind of analogy that is done with the sand dunes. So if you go on a beach, you expect, let's say, naively, but this is not the case, to have the slopes of the sand dunes to be randomly distributed. But then you realize that this is not the case, because you have the wind and you have gravity, and therefore the slope is kind of fixed around some value between 30 and 35 degrees. And therefore people started to think that maybe there is some force in the multiverse that leads the universes towards, let's say, instability, but then the unstable universes will just pop up and then die. And so the most of the universes left are basically those near the critical region. So there is a kind of a pressure, if you want, towards instability, but then there is a selection given by gravity that leads universes at the end, those that survive, to live near criticality.
Okay, so basically with the analogy, I really like this, with the analogy that you said about the beach and the dunes of sand, is that they observe, when one goes to the seaside, then the observer sees those dunes that have, let's say, prevailed, that have remained, that conditions were such that they could stay, they could, they could keep on going. Whereas you don't see those dunes such that conditions were not, let's say, were not, were not favorable for the continuum of the universe. And so the thing is that with this analogy, we are not observing the dunes from the outside. We are within the dunes, observing the dunes that, let's say, stayed in place and kept on forming. So, okay, I I understand why people tend to like or do struggle when thinking about this kind of question, because it is very challenging and really pushing yourself, at least your conventional thinking, towards boundaries which are very, very far from common sense, let's say. But I think this is very fascinating. What do you think? What do you think about this? Do you think it is just proxy speculation that may work, may not? But
so I think it's nice that people also try to think to this. It's, I think, more on the metaphysical or philosophical side. This is my belief. So I think it's really important that people try to come up with this kind of idea, which are interesting per se. But at the scientific level, so then, let's say, having some way to test this, probably this becomes more challenging and at least now I don't think there are ideas on this. So I think it's really amazing to have this kind of thought. But yes, I think there is some separation between
science and yeah.
I don't want to say that is not science, but is, if you want, science in a much broader sense compared to what we try to do, for example, at LHC. So you have a prediction, you have something that you want to test. This is a more metaphysics at this point, which is very interesting, but yes.
Yeah. And I want to let's say I want to ask you, at CERN, what do you, let's say, which breakthrough do you expect to come, let's say, in 50 years?
Breakthrough.
I mean CERN to, let's say, gather all particles accelerator, let's say, existing. Meaning, what do we expect to find? Because I watching some videos and reading about it. People are saying, I mean, the standard model, that's it. We are not expecting to find completely different, completely new particles. The particles that had to be found were found. And so, do you think we are at sort of a critical point that either we are going to see less and less breakthrough, or there is just much more to discover? What do you think about this?
So I would like to think to your second point more than the first.
Reasonably.
Yes. So as I was mentioning before, I think searches now at LHC go in different directions. So one is to try to really collect a lot of data and do measurements very precisely to try to see if there is any deviation. And this is something realistic in the sense that in the next years, you expect really LHC to collect incredible amount of data, because it will also go to a new phase called high luminosity. And therefore, you can test very well if the prediction of the standard model are compatible with what you observe, and therefore you can always try to push up, if you want, the physics, the new physics scale that you can probe with this machine indirectly. On the other side, there are a lot of also searches which are unconventional, and from them I also expect a lot. So in my case,
we are searching for the multiverses.
Now, if you want, for example, dark matter searches or these kind of things. So this is what I'm doing right now, for example. And in that case, the idea is that you look for something that was completely, let's say, thrown away by all previous analyses. So all previous analyses, all the data taken, were not targeting that kind of phase space. And therefore, there you have all the data of LHC still collected by previous years, which are basically, if you want, not analyzed in that sense, because all the previous analyses are really targeting on specific type of signatures that can appear in your detector, but maybe are disregarding, are completely throwing away some others. And so from that kind of point of view, I think there can be some surprises. I hope there will be some surprises. And I think also there is a very large amount of effort in this direction now. So to look for unconventional signatures, maybe related to dark matter, not necessarily, but maybe related to dark matter, that can be probed at LHC, taking new data or looking at the ones collected before.
Okay. And what about dark matter instead? That you were just talking about. I was actually talking with because I go sometimes. I happen to go at Science Park, which is the the campus of the science faculties from the University of Amsterdam, and there is the Institute of Grappa, which is this center for cosmology, astrophysics. And I was talking with a postdoctoral research there, and he's doing research in gravitational waves and this kind of stuff. And basically, his advisor is Gianfranco Bertone, and he's into multi-messenger astronomy, dark matter. And I was talking with this postdoc Alessandro, and he told me that we do have very strong conviction of dark matter being the existing being something. Okay. But why is it taking so long for detect, or because it was predicted a lot of time back in the days. Okay, so it is not, the recent discovery of a couple of years ago that we still have to gather ideas and projects. It was predicted much time in the past. And so how is that we are not making any, sort of, breakthrough, practical observational breakthrough with regards to dark matter, even though our conviction and our certainties are cumulating up.
Yes, I mean, from the dark matter side, you have evidences from astronomy and cosmology, as you were mentioning before, which are quite stringent. Then the problem is how you can probe dark matter as a particle, as a fundamental particle, so those that we were discussing today, and what are the interactions of dark matter with the standard model matter. Because you know from cosmology that dark matter interacts gravitationally, but from a particle physics point of view, the gravitational interaction is not really cannot really probed at our colliders. It's so weak at the scales that we are looking at. So if you want at low energy scales, that basically it's irrelevant to try to look for dark matter manifesting as a particle through the gravitational interaction. And so what you try to do is to, let's say, build these kind of portal models. So you say, okay, maybe dark matter or this dark sector that must exist because interacts gravitationally can also interact in another way with the standard model. And so you built these portal models where you introduce other particles which mediate the interaction between the standard model and the dark sector. And in that way, you, with this strong assumption, which is not verified experimentally, okay, you try to look for dark matter and maybe to produce it in a laboratory. So what in cosmology and in astronomy do, they measure the effects of the existing dark matter via the, let's say, gravitational effects. What we try to do at LHC is to produce dark matter, assuming that there is a portal between the standard model, so our protons, and the dark sector. So this unknown sector of particles. But the whole assumption, the whole thing is to introduce further portals, which we need to try to find also. So these further portals are something additional that we need to find. If we find a portal, we can find another sector that can correspond to the dark sector, let's say. Also, this connection is not obvious in the case of colliders. So I think the whole thing is that to understand the nature of dark matter as a particle without going through gravity, which at this moment is really hard, you need some other type of weak interaction, very weak interaction, that you need to probe somehow, or with colliders, and you have to try to produce this portal and then let the portal decay to the dark sector, or with some other experiments looking for dark matter which comes from nature itself, so not let's say produced by any collider experiment, and let this interact also with some weak or portal interaction with your standard model matter. So this is the situation right now, and is fixed in this way.
Okay, don't you find you mentioned the dark matter interacts gravitationally, and we are sure about that. So don't you, at least if I think about it, and it looks sort of sneaky. Let's put it this way, sort of sneaky, that the only force through which dark matter interacts is the only force which we, with our, let's say, with our understandable and tested theories of physics, so standard model and general relativity, basically we cannot test. Or actually, meaning is not included. Meaning, okay, quantum field theory includes 3 out of the 4 forces. Doesn't it sound sneaky that the 4th one, which is gravity, is the one through which dark matter interacts? Like, to me, if I think about this, literally just putting writing it down, like I'd say it appears as if we developed the cutting edge tools, hugely cutting edge. I mean, we described a huge amount of I'd say of observation. We had huge amount of observation which testified our theories, but for a very specific case, in this case dark matter, we are just trying to randomly shovel with our sword, which is not sharp enough, because that's not the right tool to go with it. I don't know, I have this impression.
Yes, I can share, let's say, this impression too. This is, I think also there is something that is not completely understood related to gravity and dark matter itself. But at this moment, I think, we are still, let's say...
It is what it is.
Yes, at this moment it is what it is, and we have no idea of how to change, at least in my case, this. So yes, I mean, probably there should be some also, why not, a conceptual breakthrough in this sense that we can try to expect. But the situation is quite static in what I have described before. So people are really are hoping to find dark matter in this kind of way.
What do you think about? I knew that WIMPs were quite a good candidate for dark matter. Do you think they are suitable, or do you think there is some other more suited candidates for dark matter?
So people were basically trying to look for dark matter for many years with these WIMPs. But there are very strong constraints coming from previous searches, direct and also collider searches for WIMPs. So maybe people now are like going in some other direction, trying, for example, to look for dark matter let's say in another type of dark matter, maybe a composite dark matter state, which lives in a so-called hidden valley. So this is the full class of hidden valley models, where basically you try to introduce some gauge group for the hidden sector, which is very similar to, let's say, SU3C, so one part of the standard model. And that hidden sector creates basically composite dark matter. And then still you hope that part of this composite dark matter can decay back to the standard model via some portal. So the concept of portal itself remains the same, but these hidden valley models at collider level, for example, allow you to access, as I was mentioning before, signatures that WIMPs cannot generate. And therefore, you hope that basically some part of the phase space which should remain still available for these kind of dark matter models, because the signature was not tackled from any analysis, for example. This is a possibility. Yes, but
okay.
But still, we are very vinculated to the portal paradigm, and yes, this is the main point. I mean, we have a natural portal that we know very well, which is gravity, but still, at the level of particle physics, gravity is something really
not explained. Yes,
pure.
Okay. And do you, let's say, I wanted to conclude with let's say, with a question and a related explanation of why we do want to love the Higgs boson, why we do want to care about the Higgs boson, because yeah, maybe it is much more common to hear about electron, some other quarks, some other type of fundamental particles, but why was the Higgs boson fundamental in the very early universe? And let's say, how without, because the intuition that I have behind it is well, okay, without a Higgs boson, or with a Higgs boson, let's say, brutally of zero, we would have no mass. Mm-hmm. So why do we want to care about the Higgs boson? What was his role in the very early universe? And did it have let's say, a leading role in what came to be known as our universe today.
Yes. So I think this is indeed a good point. I mean, basically, the Higgs boson itself gives mass to everything that we know. So without it, we would have a very, very different reality. So this is one of the major points. And that's why we want to try to understand better this Higgs field and what was the role, as you were mentioning, in the early universe, because probably at the very beginning, with very high temperatures, the situation in terms of how the initial symmetry of the standard model was living basically was different compared to today. So in the very early universe, maybe that symmetry was not broken, and then with the evolution of the universe, we had a phase transition, this so-called electroweak phase transition, where basically the Higgs field acquired a non-zero vacuum expectation value, so ended in one of the holes of the potential, and therefore, let's say, studying this is fundamental, and this is also what we are, let's say, trying to do at LHC in some sense, trying to probe better the shape of the potential, which is really the major unknown in the Higgs sector. So there are really a lot of questions related to the Higgs sector and how the Higgs sector relates to the standard model. But the very evident one, let's say, when you look at the Lagrangian here, this one, you know all the terms, and then you go to the Higgs potential, and the Higgs potential in the standard model is just given, is like that. But we are not really sure that the potential, the real potential, is that one. So I think now a lot of effort is, let's say, also going in the direction to understand better what is the shape of this potential. So the high luminosity phase of LHC will let me go to the thing. We'll try to tackle, let's say, this problem of the potential, trying to measure, for example, how the Higgs interacts with itself. So there are some processes like double Higgs production that are very difficult to measure because there are some technical issues with, let's say, interference between different processes that takes the whole probability of producing two Higgses very low compared to other processes that we are trying to tackle at LHC. But this is, for example, one of main justification for high luminosity. So it was shown that in high lumi phase, LHC will be able to measure with, let's say, better precision this coupling of the Higgs with himself, and so get major, let's say, more knowledge regarding this shape of the potential. And the shape of the potential, as I was mentioning before, then is really connected with this electroweak phase transition. And the if let's say we find something unexpected in the potential, so different from the standard model, this should appear as, for example, a first order phase transition and therefore this would imply the existence of new physics, new particles that enter in the picture. So everything, let's say, studying the Higgs is really a very good test, both for our understanding of the standard model, but for these reasons that I'm mentioning now, is really fundamental also to access in different ways the BSM physics.
Okay. So overall, we want to care about the Higgs boson. We do like the Higgs boson. Let's not discriminate it, and let's give him the same importance as the other bosons and particles. Okay.
Yes. So, let's say, at the end, is one of the fundamental building blocks of our standard model, and is fundamental for what we observe and the reality that we observe.
Great. So, yeah, I think we can wrap it up here. Cesare, thank you very much for your slides and all your explanation. It was
I mean, I tried really to also share this kind of slide because I knew that was kind of hard to explain some concepts without having at least something in front of your eyes. And also mine, because
absolutely. Yeah. So thank you very much again for your time and your explanation. This was indeed our episode, and we can end it here. Thank you, Cesare, again, and good luck with proceeding your studies and at CERN. So maybe in the future, as soon as some breakthrough comes out at CERN, you may come back and talk about them. So it would be fun. So thank you again, and thanks everyone for listening along with us. That was Math and Beyond. Thank you for being with us. I will see you soon. Ciao.